This is AP Calculus AB Session B. Welcome to the new semester, Lesson 1. And we are estimating with finite sums. The topic is the definite integral. So we're going to learn something called the fundamental theorem of calculus and some other things here in this unit. It's a loaded lesson. The second semester really is all about the antiderivative or the integral. The first semester is all about the derivative, the rate of change. But now we're going to be talking about the derivative, the antiderivative, the integral, and the area under the curve. So without further ado, let's go ahead and graph a function here. I'm going to say y equals x minus 2 and x minus 5. X minus 2 times x minus 5. As you know, that is a parabola with x-intercepts of 2 and 5. 2, 3, 4, 5. Okay, and actually, I'm going to go to 6, just to make it that much easier. All right. So we can focus on the concepts here and not the arithmetic so much. Okay. All right, and so I want to know the coordinates of the vertex. So the vertex occurs at 4. 4 minus 2 is 2. 4 minus 6 is negative 2. Negative 2 times 2 is 4. Okay. And actually, I'm going to, well, let's leave it. Yeah, let's put a negative in front. So a negative in front so that it flips it upside down. But it's going to go through 4. Okay, and so we have a parabola here. First term is x squared, so down 1, down 4, down 5, etc. Okay, there's our shape. And I'm interested in this case of finding the area under the curve. Now, if I were teaching a very basic class, I might use this approach. Why not count the squares under the curve? And in this case here, I need to be more specific. I'm looking for the area under the curve between the x-intercepts here. It can really be between any two values, but between the x-intercepts. Okay? And so I could count squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, yeah, it looks to me to be about 10 or 11. All right, and that's an estimate. But there's a more precise way. There are several more precise ways. What it comes down to is 3 methods in this lesson that we're talking about. LRAM, that means the left rectangular approximation method. RRAM, right rectangular approximation method. And MRAM, or midpoint rectangular approximation method. The idea is this. We divide the domain that we're talking about from A to B, in this case from 2 to 6, into regions. Okay? So we're going to divide this into 4 regions here just for the sake of convenience, but it can be any number. Okay? And we're going to find LRAM. Let's do LRAM first. LRAM is the more common of the two of them. Okay, and basically the idea is LRAM says for any boundary that we've got, we're going to take the height of that boundary, the height of the rectangle there, as that boundary. So the height of the first boundary is 0. The height of the second boundary is 3. The height of the third boundary is 4, and the height of the fourth boundary is 3. Okay, and so we're going to take the sum of each one of these, right? Now, in this case, the width is 1, so it's kind of irrelevant here, but there is 0 area, followed by 3 area, followed by 4 area, followed by 3 area. If the width had been 2, we'd be multiplying each of these by 2. If the width had been 3 for each rectangle, we'd be multiplying each by 3. Okay, but the total area under the curve is 0 plus 3 plus 4 plus 3, which is 10. Okay, so I estimated 10 or 11 or so. Okay, that would be the LRAM LRAM method. Left rectangular approximation method. Okay, and we can do this. We can do the right rectangular approximation method. Let's see if it'll allow me to undo all the way back here. There we go, luckily. Okay, so now the right rectangular approximation method takes the height of the rectangle as the right boundary. So the height of the first boundary would be 3, the height of the next would be 4, the height of the next would be 3, and the height of the last would be 1. So we have 3 plus 4 plus 3 plus 1, or not 0, not 1, 0, plus 0 again equaling 10. So this is what we call RRAM, right rectangular approximation method. Okay. The midpoint is a little more complicated, so let's do it here. All right. So the midpoint says let's take, for the height of each band, the midpoint of the domain. So I'm going to take the value at the midpoint, which is 1/2. And what is the height at 1/2? What is the height at the midpoint between 1 and 2, or 1.5, or 3/2? What is the height at the midpoint or 5/2 of the next one, and the midpoint of the next one? The midpoint is 7/2. 7/2, not, or 5/2, not 5/5. Okay, so we're finding the middle of each boundary and finding the function value for that particular one. That takes a little more calculation here. So let's do a table x, x equaling 1/2 or 0.5. And we have 0.5 minus 2, which is negative 1.5. And 0.5 minus 6, which is negative 4.5. And that's negative in the front to make it positive. And actually, no. Oh, duh, because I gave the wrong value. It's not 0.5. I was going to say, that doesn't work. It's because the value here is 1, 2, 2.5, right? Let's back up. So the midpoint of this boundary is, I was counting it like it was from 0. This is 2.5. This is 3.5. This is 4.5. And this is 5.5. Okay? So we're finding the values at those. So x, 2.5, 3.5, 4.5, 5.5. Okay? Y, 2.5 minus 2 is 0.5. 2.5 minus 6 is negative 3.5. Negative is positive. Half of 3.5 is 1.5, and 0.25, 1.75. So the height of this rectangle is 1.75. 1.75. Okay, height of the next rectangle is 3.5 minus 2, which is 1.5. 3.5 minus 6, which is negative 2.5. 1.5 times 2.5, half of 2.5 is 1.25, 3.75, 3.75. Okay, and that works out here, 3 3/4 at 3.75. So the area of that rectangle is 3.75. Okay, the next one, negative. Okay, 4.5 minus 2 is 2.5. And 4.5 minus 6 is negative 1.5. That's going to be positive 3.75. Okay, and negative. And then 5.5. 5.5 minus 2 is 3.5. And 5.5 minus 6 is negative 0.5, which is 1.75. Okay, or 1 3/4. So 1.75, 3.75, 3.75, and 1.75. Adding them all up. 1, or I'm just going to do it over here. 1.5, 1.5, and 1.5 is 3, 4, 7, 10, 11. So we actually get 11 out of MRAM. Now here's the question, which do you think is more accurate? I think MRAM is a good estimate. You're usually gonna find MRAM to be more accurate than LRAM or RRAM. All right, so hopefully that makes sense. Let me know if you have any questions. Do know that the boundaries do not have to be evenly spaced. Do remember that I did simplify this, so remember we're taking delta x times f of whatever the x value is, x sub I. That is the area of that slice, delta x times f of x sub I. Whatever the x sub I is, if it's the left value or the right value or the midpoint value. Okay? All right.